We have for a perfect gas the ideal gas equation of state, which we know very well by now. PV is equal to nRT. And instead of writing it in this fashion, I want to just change it a little bit and write it as PV over nRT. And of course, if I take everything over here and put it on the left side, what am I left with? It should equal 1 for a perfect gas. But instead of writing 1, I'm going to write Z. And Z has a name. This is capital Z, not small z, which is collision frequency, but this is a compression. This is the compression factor. And it's a capital Z. Now, we talked about intensive and extensive properties. Volume is an extensive property. It scales with the addition of stuff. It depends on how much is there. And if I divide volume by the number of moles, I get something called a molar volume. And that just makes this equation just a little bit neater. And so a molar volume is PVM. That M is a subscript. So I'll say PVM, but what I really mean is PV subscript M. And that's divided by RT. So PVM over RT is equal to my compression factor. So indeed, Z is equal to 1, exactly 1, for a perfect gas. Up until now, we may have heard about an ideal gas, but the terminology in the current textbook that we're using talks about a perfect gas. All right, so for a real gas, where we're going with this is that Z might not be equal to 1. It could be a little bit greater or it could be a little less. And first of all, I want you to consider what are the units? What are the units of the compression factor Z? Does it have any units? Well, no, it actually is a unitless factor. Okay, so no units. So that means that if we were calculating Z from pressure, volume, and temperature information, we want to make sure that all the units cancel. And then we know that we're on the right path to solving that. So for real gases, Z is close to 1, but it can be a little bit greater or a little bit less. So for real gases, what do we have? Z can be greater than 1, Z can be less than 1, and in some rare cases for a real gas, Z is actually very close or equal to 1, but we'll get to that in a minute. And what does that depend on? A couple of things. This depends on the gas itself, and to some extent it depends on the conditions. Okay, especially pressure. And we'll see that in this video. So how come real gases do not have this expression equal to 1? And I think we can very quickly state that in a real gas, the particles do experience intermolecular forces, and that has a real effect on how well this ideal gas equation of state or perfect gas equation of state actually applies. We talked about it being a limiting law already. So for a real gas then, particles, we say particles, but these are gas molecules. Particles do experience some interparticle or intermolecular forces. All right. Okay. So, let's say that this real gas has net attractive forces. Net attractive forces going on. I want you to predict the value, at least the direction, of Z. So what would it be? Is it going to be greater than 1, less than 1? The gas has net attractive forces. So let's think about that. Let me turn the page. Okay. So let's go back to the statement. So PVM over RT is equal to Z. Now, if the gas is experiencing net attractive forces, what can you say about the observed volume relative to the predicted or ideal volume according to the perfect gas equation? So I have a symbol for that. This is, let's say, the ideal volume. And that ideal volume is the value that PVNRT would actually predict, right, using the ideal gas equation of state or perfect gas equation of state. So Vm by itself, without the little sign, is the real volume. So if the gas is experiencing net attractive forces, then think about the volume that it actually occupies as compared to the volume that's predicted. Would it actually occupy a larger volume if the particles have a net attractive force for each other? Vm would actually be a little bit less than what's predicted. Okay, so what effect does that have on this equation here? If this is a little bit less than predicted, then this value is going to be a little bit less than predicted because the molar volume is on the numerator. And ideally, Z is equal to 1. So therefore, for a gas that has net attractive forces, Z is going to be less than 1 under those conditions. All right. And similarly, if we take another example, so for a real gas that's experiencing a net repulsive forces among its molecules, then what we observe is that the molar volume observed is going to be slightly greater than that which is predicted by the PVNRT equation, and therefore my Z value is going to be slightly greater than 1 in that case. So that leads us to another expression for the compression factor, which is a really convenient one. If I simply take the ratio of the observed molar volume, or the real molar volume, to the predicted or ideal one, that ratio, does it have any units? No, right? It doesn't have any units. It's volume units over volume units. It does not matter what units I use for volume to compute this ratio, so long as the units on the top and bottom are the same, because to convert among the different units of volume, it's all multiplication, so I maintain that ratio. So this is another expression for the compression factor. So maybe we're starting to get an idea of why it's actually called a compression factor. And so let's make sure that this way around makes sense with what we've just stated here. So, for a gas with net attractive forces, the observed molar volume is slightly less than predicted. That's going to make this guy slightly less than 1. Got it. And for repulsive forces, this would be slightly bigger than this, which would make this slightly larger than 1. Okay, so if you reason your way through, you will not, hopefully, get this thing upside down as an expression for Z. Good. And remember, Z is a unitless factor, compression factor. Right, and so its name, compression factor. So we have easily compressed gases, and so easily compressed gases have their Z value, think about it, slightly greater or slightly less than 1. An easily compressed gas, like propane, very easy to compress. Think about it. Think of your propane gas tank. What do you do when you if you don't have a gauge? In the absence of a gauge, what do you do if you're wondering if you have enough gas left for a barbecue? You give the tank a shake and you listen. And normally gases don't make a sloshing sound, so clearly your propane is easily compressed, in fact condensed down to a liquid, so that's what we're hearing there. So we would predict that the Z value for propane is slightly less than 1. Well, let's advance this page. And let's actually sketch. Let's put that in view. We can actually sketch, and this is one of the learning outcomes you need to be able to achieve. Let's sketch the dependence of the compression factor for different gases with pressure. All right. Our reference point is, I'm going to draw it as a dashed line. Our reference point is 1.00. So normally the Z factors, or the compression factor or value of Z, it's written with 2 decimal places. So normally 3 sig figs. And so let's make our reference point 1.00. So in fact, this Z would be for a perfect gas. All right, what would this function look like for a gas that has net repulsive forces all the time? And our exemplary gas there is H2. And here's what it looks like. It takes off from 1 and just goes straight up. So that's what the hydrogen gas looks like. The Z value is greater than 1 for all of these pressures. Now for an easily compressed gas, we have something like this. But it can't keep descending, because think about it. If the pressure is getting greater and greater, at some point these molecules have to exhibit net repulsive forces. And so even for these, they ultimately do this. Okay, so to about here, net attractive, and then it starts going up. So for this, we have a compression factor less than 1, and then increasing to 1, and then finally increasing above 1. And so this one, I'll label it up here, but this would be net attractive forces, and this is net repulsive forces. That would be my sketch of the compression factor for these 3 gases. The perfect gas, a net attraction, but ultimately going up, and net repulsive forces. And so I'll have you look up in the textbook or online, whatever your resources are, what this looks like for propane, and you can imagine there's a good dip. Carbon dioxide is a pretty easily compressed gas as well, and it has a funny peak in its dip and then stable before it ultimately creeps up, but you can look at those in your textbook or whatever resource you're using. Another way we can look at this is to examine the function, the dependence of Z with pressure for, see, these were different gases, but now I want to consider it for just one gas, but at different temperatures. So let's use this set of axes to represent one gas, but at different temperatures. And whenever you sketch one of these, you always want to make your reference point 1.00. You can label your axis over here 1.00. And let's start easy. If I go to a really, really high temperature, what do you think is going to happen intermolecularly with a really high temperature? Even if there are attractive forces occurring in the gas, if you pump in enough thermal energy, those attractive forces are going to be overcome. And we know this well. It's the principle behind boiling. And so for a gas that exhibits net attractive forces at a high enough temperature, and I'm going to put this one, and we're just doing examples here, so let me just start us off with 1000 Kelvin. Okay, I expect that compression factor to be above 1, even at low pressure, and certainly with increasing pressure it's only going to grow. All right, and then let's take the other extreme, like down at 200. 200 might look something like that. And somewhere in between, something like this. And maybe that's 600. And now I want to do one where it's behaving ideally and then it takes off. And let's say, these are all examples, right? This isn't a real situation. But it could be a gas. I just don't know which gas this is. See right here where it is equal to 1 over at a low pressure and over an extended pressure range before the net repulsive forces take over. So where you have a real gas behaving like a perfect one in terms of its compression factor equaling 1, that temperature, it only does this at one temperature, and that temperature is called the Boyle temperature. And so at a gas, and every gas has a Boyle temperature, you can look it up in a table. So at the Boyle temperature for a given gas, it actually behaves ideally over an extended pressure range. And this is really important because even though it's a real gas, I can predict its properties very well using the simplified PV-nRT equation. Right? So just so long as I can predict it, so long as I am working at that temperature in 500 K. So that actually has some practical applications that are quite important. Okay, just checking my notes here. So under conditions of low pressure and low temperature, it makes sense that we can summarize that attractive forces will dominate. And under conditions of high temperature, those attractive forces are overcome. And under conditions of high pressure, well, we've got finite size effects are a factor, and so we have net repulsive as well. Okay, so what I will add as a note here for the Boyle temperature, what can I comment on about the slope of this line right here? Not the whole function, but just in this range. in this range. And how would I write the slope mathematically? And we want to get away from delta. We want to think d, okay, because it's over a small range. Well, at the boil temperature, dz by dp, so there's my rise over run, at that boil temperature is equal to 0. My slope. I don't have a slope. It's a flat line, not a straight line. Okay, it is straight, but it's also flat. So it is a flat line, or dz by dp is equal to 0. Okay, let's stop there.